Now let's analyze the vertical problem of the pilot doing a vertical loop in his plane. Let's start by looking at the bottom of the loop first. So here we are at the bottom. We're coming around. Let's draw a picture. I'm going to ignore the plane. We know it's there. Here's a picture of the pilot sitting in his seat. We're ignoring things like seat belts because that just makes the problem have more forces. So there's the pilot at the bottom. Now remember, the pilot and the plane are both doing a loop following a circular path. So we're going to have to pick the form of FC we're going to deal with, because anytime we have an object following a circular path, we need centripetal force. So we'll start with this. And it makes most sense to use the form of FC as mv squared over r, because it makes more sense that we are going to deal with a velocity of a plane versus the angular velocity. So now what we have to do is draw the forces acting on the pilot to do the sum F. Remember, don't look at FC anymore, just sum forces. Well, the forces on the pilot, look, mg down, and the force of the seat on the pilot pushing back on the pilot, which is the normal force N. And in this problem, that's what we're looking for. That is the force of the seat on the pilot. You sit in a chair, it pushes back on you. In this case, that's the normal force. Toward the center is positive. Now, N has to supply all the centripetal force, but it also has to fight gravity, so it means it's going to be bigger than just FC. But let our equation tell us this. So let's sum the forces and then see what happens. When you do, you get N minus mg on the left. And now we look, N is the only thing supplying FC, because N is the only thing toward the center of the circle. And here's what we end up with. What we just mentioned, the N should be large. N is mv squared over r plus mg. What it means is the normal force has to supply the centripetal force and fight gravity. This is the actual answer to the problem. If you actually had numbers, you could solve. But let's kind of analyze it a little further to see what it means. So N is, I'm going to factor out an m, v squared over r plus g. Well, the terms in parentheses are both accelerations. In fact, m, this is centripetal acceleration, and this is the acceleration due to gravity. Make sure you always use positive g in this case. But look what we have. I want to analyze this term. You may have heard of the term a pilot pulling G's. This term is what you call G's. That's the acceleration the pilot feels. Now, why are we calling it G's? Well, let's just think. If AC was calculated to be, based on numbers, the number 9.8, that's a G. 1G and 1G is 2G's. If v squared over r was 19.6, that's 2G's. Add another G, you have 3G's. So this is what we actually consider how many G's a pilot feels. And conditioned pilots can probably handle for a short period up to 7 G's. We would be passed out at that point. We can handle 2, maybe 3 G's. Conditioned pilots can probably handle about 7. Got to be careful that the plane can handle all of that, or the plane may decide it wants to fall apart. So what do we really look at the bottom of the loop for? Yes, we can calculate the force, but the bottom of the loop, this is its claim to fame. It is where N is a maximum. N reaches its largest value at the bottom of the loop. So it could be N in this case, or if it was like a rope swinging a bucket of water in a vertical loop, at the bottom of the loop is where you would want to make sure the rope wasn't going to break. That is where the tension in the rope would be a maximum, which is equivalent to N in this problem. So anytime in a vertical problem, if you are looking for something that deals with maximum force or will the rope break, you are analyzing the bottom of the loop.